Great. Hi, everyone. Welcome to GOCC. We're very happy to have Dr. Yannic Vergas come give an expert talk for us. Before we get started, I just want to remind us of our community statement. It's that we're all learning, everyone has something to contribute, and no one has all the answers. But with that, let's take to Yannic.
Thank you very much, Anastasia. Thank you so much for the invitation. So this Graduate Online Combinatorics Colloquium has been ongoing so far a couple of years. So just congratulations for this. This is a very nice ambient to give a talk and to also to hear about nice talks related to combinatorics. So my what I want to show you today is some partial works, ongoing work related to this, let's say, new field called non-commutative probability. What I'm going to do today is show you why, essentially, why I start to look at this area. Essentially, because there is a lot of algebraic combinatorics involved. I will say a couple of words at the end of my talk. There are this community of mathematicians working around non-commutative probability, for which there is a lot of combinatorics. And of course, there is this community of people doing combinatorics. We are not aware of this field. And just to tell you that there is a lot of interacting work in between both communities. So hopefully I will give a talk in less than 97 hours, not as the title of this book. Part of this work, again, is a joint work with Adrián Celestino. So part of the story is on this paper, on this article on Archive. And what I'm going to do is again, talk a little bit. I will give you a motivation on how and why I started to look at non-commutative probability. So again, I come from algebraic combinatorics, more precisely from looking at combinatorial Hopf algebras. And that's essentially the reason why I started to look at non-commutative probability, because there is several results in non-commutative probability related to using tools from Hopf algebra and combinatorics. So that's what I'm going to try to show you today. And so let's start. So let me start with this very naive question that combinatorialists used to like. So I just give you a sequence of integers, and I can ask, what do these numbers represent? What do they count, right? So this is a very natural combinatorial question. If you come from probability, you may ask, for example, is this a sequence related to some moment or some cumulant? The reason is that under certain condition, a sequence of moment determine a distribution, okay? And there is a very near link between sequence of moment and sequence of cumulant that I will emphasize in a moment. So from the probability point of view, this is called the moment problem, and is quite standard in the theory. It has a solution in the sense that you can say whether a sequence corresponds to a sequence of moments. You just have to look at the Hankel matrices associated to the sequence and look if they are positive definite. So I'm not going to talk about Hankel matrices, essentially a sequence of matrices constructed from the sequence. And then you look at this condition of positive definiteness, and then you will know if this sequence is a sequence of moments or not. So I'm also have to say, so there is a lot of terminology from probability here. I will just give the basic ones because I'm not coming from probability. So maybe Also, please stop me if there are any questions, but if there are questions related to probability, I will try to answer, but just to let you know that I'm more from the algebraic part than the probability part. Still, try to work together with both areas. And the precise goal of this talk is to understand the sequence of moments studied in probability from a combinatorial and algebraic point of view. So that's will be the main goal of this talk, and also one of the reasons why I started to look at this area. So let me recall some basic facts about moments. So if we start with random variable x, with distribution psi, the moments can be. Can you see the mouse? Yeah, okay. Can be described in terms of this integral if it exists. And then you can look at the formal Laplace transform, which is this integral, which is in fact a generating function, and not any generating function, is an exponential generating function constructed from the sequence of moments. Okay? We can, if we take the logarithm of the formal Laplace transform, we get another generating function, which is also, we can write in exponential form, for which the coefficients are the cumulants. So k of z is the exponential generating function for cumulants. And then there is a relation between the exponential generating function from moment and the one from cumulant. So this equality, this relation between moments, is very well known in combinatorics. It's called the exponential formula. And this will be one of the main link between the relation between moment and cumulant in non-commutative probability with combinatorics, or one of the links that I will try to emphasize during my talk. So again,
Yannic,
yes.
Oh, 1 second. There's a question in the chat from
Sure.
Michelle. So you're interested in hamburger moments sequence specifically?
I don't. So hamburger moment sequence are a particular sequence of moments, right?
So you're like, what is the domain you're interested in? The entire real line?
Let's see. I think so the can be the real line, yes, but I will show you a more general example of sequence of moments. So it's not only that one. Yeah, let's say for the moment is more than these type of sequences.
Okay, thank you.
Okay. All right. So again, we have this formula, the exponential formula. And if we develop the formula, we expand the exponential, and we look at the relation between the sequence of moment and the sequence of cumulant, we get to this identity here. So this identity say that so on the right-hand side, we have a sum. The sum is over partition. And here I'm using an order on partition, the refinement order. Here we see this m pi kappa tau. So pi and tau are partition. And what I mean by m pi, for example, I mean the product of the term of the sequence of moments indexed by the size of the block. So if pi is a partition, which k block, m pi just means the product of m sub size of the first block times size of the second block, and so on. Same thing from kappa pi. So again, this order corresponds to the refinement order. So the set that I'm partitioning, the set 1, 2 through n. And the link, again, between, so here I show you this relation between the sequence from moment, the sequence from cumulant, and you can reverse this relation using the Möbius inversion. So if you write, so if you take this n here is for you obtain this n here where you take the particular partition being the partition with n blocks. No, with just one block, sorry. So with just one block formed by the n elements, so that will give you this n here. And then you have to take, and this will be the minimal element in the poset. So the sum, this sum here becomes a sum over all partition of pi n. So that's where this equality comes from. Okay, this equality comes again from taking this pi being the minimal element in the refinement poset. Then again, you can invert this by Möbius inversion, and then you also have a relation between, you have a formula for kappa n in terms of the term of the sequence. So here's an example on how the formula looks like. I didn't ask, so is everybody okay with the Möbius function? Okay. So the Möbius function on a poset is a function defined recursively. So for example, let me just say that if I want the Möbius in blue here, I'm indicating the Möbius function from the minimal element to the selected term. So for example, here, the Möbius function here is 2, meaning that I'm looking at the Möbius function on the interval from 1 to 3, 4, the minimal element of the poset to this poset. Okay, and what must happen is that the blue values must add 0 when I add all values of the interval between this element and this element. Okay, and this is just an example of calculation of, for example, how you look at kappa 4. So again, kappa 4 will correspond to this partition with 4 elements, and then you take the Möbius, you look at the Möbius value and you get these terms. All right. So now let's play the following game. So I gave you a motivation from probability, in the sense that I showed you in probability you have those two sequences which are very related one to the other, the sequence of moment, the sequence of cumulants. So what you can do is forget about probability for a moment. I give you a sequence and you perform the same kind of transformation that we do to look at cumulants in terms of moments, meaning that I give you any sequence, you look at the exponential derivative function of the sequence, take the logarithm, and you construct a new sequence, looking at the terms of this exponential derivative function. This is sometimes called I think it's called the exponential transformation or the logarithmic transformation of a sequence in theoretical informatics. And so here what we want to do is to play the same game from any general sequence. So from any general sequence of terms an, I'm going to construct the sequence of cumulants, the classical cumulants. Okay, so what I'm doing in this definition is doing exactly this, showing you exactly the same kind of relation between the sequence of cumulants and moments. And now I can play the game again using different posets. So I will call the free cumulant sequence the sequence of terms constructed in this way. Here the poset has changed. I'm now considering the poset of non-crossing partition that I will show you in a moment. And another sequence that I would be interested is the sequence, the boolean sequence, for which here again I change the poset. It's not the poset of partition anymore, it's another one. So, and here the notation works as before. So f of this partition just means the product of every sequence related to f indexed by the size of the block. Okay, so that's where you see f of pi is exactly this. So what I'm going to do now is explain you why I want to look at those sequence and what kind of interesting combinatorial algebraic result we can look at from those identities. So the first sequence, I can say, well, it's motivated by the relation between moments and cumulants in classical probability. And this free cumulant sequence and this Boolean sequence is motivated from some non-commutative independence on this field called non-commutative probability. So that is what's coming next. Before, let me introduce you this couple of posets. So the poset of non-crossing partitions. So it's a classical partition of a totally ordered set 1, 2 through n, which not satisfy this condition. So we do not want to have two blocks, bi, bj, such that two elements on Bi, P1, P2, and two elements on Bj, Q1, Q2 are related like that. So if we draw a picture of those blocks, that will indicate that we have some crossing between the blocks. Okay, so I will denote by NCM the set of non-crossing partition. So here's a very simple non-crossing partition. And NCint denote the set of the so-called interval non-crossing partition, which means a non-crossing partition for which every block is composed by consecutive integers. So here's an example. The second non-crossing partition is an interval non-crossing partition. The first one is not. And you can think on interval non-crossing partition essentially as composition of a integer, right? So this is equivalent to the composition 1, 4, 1, 3. Okay, being a composition, a word on a non-negative integer or positive integer. All right. So here's
in the previous example.
Yes.
Yeah. So the first one is is that a non-crossing partition?
The first one is non-crossing. So
Okay,
this non-crossing partition has 1, 2, 3, 4, 5, 6 blocks.
Right. And so one of the sets is 1, 9, and the other one is 2, 3, 5.
Exactly.
So that means we have 2, 5 in between 1 and 9, right?
Yes, yes.
So it is non-crossing if we do not have the condition given.
This condition here. So let me maybe make a picture. So this, for example, is a crossing partition. So if I have something like that, let's say this block, okay? So I have two blocks, the block 1, 3, the block 2, 5, for which there is two elements, which are 1 and 3, and two elements 2 and 5, which satisfy this condition. So this is P1, this is, oh, okay, there's a typo here, I think, which what I want is P1, Q1, P2, Q2 maybe. So this is P1, P2, Q1, Q2. Yeah, so forget. Is that okay?
Yeah, that makes more sense now.
Yeah, sorry, yes. I never get on this typo. I'm gonna
It's okay.
write it down. Yeah.
For a second.
Yeah. Thank you very much for the indication. Any other question? Okay, so let me continue. So we have non-crossing partitions, we have interval non-crossing partition, we also have the classical partition. So those three posets are very nice combinatorially. So the size, here the size, classical partition counted by Bell numbers, this non-crossing partition counted by Catalan number, and non-crossing interval partition, again, those are composition of an integer, so they counted by this power of 2. And very interestingly, the Möbius function is also very nice combinatorially. So for instance, on the poset of non-crossing partition, Catalan appears on the size point of view, and also when you calculate the Möbius function. And those three posets are three very rich combinatorial objects that appear in the study of this free non-commutative probability theory. Okay, let me, right? So again, here are the definition of this new sequence from a fixed sequence. I also can say, may say that this formula encodes some notion of connectedness that I will talk at the end of this talk, okay? So again, the purpose of this talk, let's say, is to understand those identities. Now let me show you where does this come from. So let me start with that. I like to start with this kind of example because it's a toy example, which is very combinatorial. So the ingredients here, or the main ingredients here are rooted graph. So we're going to work with rooted graph, finite simple rooted graph. And the idea is that we want to look at closed walls of some length, starting at the root and ending at the root. And in order to, we can count the number of closed walls in a rooted graph, looking at the adjacency matrix. So what do? You construct the adjacency matrix, which is a finite matrix because J is finite. And you take, so here again, it's a typo. It should be, you take the power n of the adjacency matrix and then look at the entry 1, 1 of that matrix. And that's give you the number of closed walls starting at the vertex 1, 1 and ending at the vertex 1, 1, at the position of the matrix 1, 1, which correspond to the vertex 1, V1. So if V1 is the root, then that corresponds to the number of closed walls of the length n, starting and ending at this root. All right. So now the idea is to consider a space of to relate this counting problem with some probability, considering a space of random variable, where the random variable here are all possible matrices that comes that are the adjacency matrix of some graph. And in that case, the expectation of the n power of this random variable, which are matrices, will you can define it as this number. And this appears on the study of growing graph, for which you have some process of graph which are growing on the time, and the way they are growing is through some operation that I'm going to show in a moment. And what we are interested in is to look at this expectation, which correspond to the number of the expectation of having the number of closed walls of certain size, assume the graph is growing on and growing on. So let me show you in practice, what I said is correspond to calculate this expectation. So let me show you a couple of operations between graph related to this growing graph topic. So Cartesian product, the classical Cartesian product. So I take two rooted graph and I construct a graph in this way. So the rooted vertex of the new graph is just the superposition. I mean, it's the one considered by superposing both rooted vertex. And there is a way to calculate the adjacency matrix of the Cartesian product of two graphs. Is given by this formula. So here there are two notions to see here. This is the Kronecker product between matrices, which means you take, so I can make an example. So you take A, B, C, D, and times A, let's say, time matrix A. And then, so what you have to do is to multiply every component of the left factor by A, and then you expand. So this new matrix will have the double size of the matrix A in this case, let's say. Okay, so this is the Kronecker product. And this A1 and A2 correspond to the identity matrix of size, the size of the adjacency matrix of J1 and J2 respectively. So we have this formula to calculate this adjacency matrix, and then when we're going to look at the expectation of the n power of this matrix, well, this we can show that in fact, these two matrices commute, and then when you do the calculation, it's just this sum over this binomial coefficient of this product. Okay, so let's say that it's not hard to calculate the expectation of this n power of this matrix in terms of these two, just because they will commute. Okay. Now let's look at another more elaborate example, which is the star product. So for the star product, what I'm doing is just superposing the root in a planar way, in the sense that, so here I will say that the second factor, this graph, which is a triangle, is to the left of the square. Here I draw it like that because you can realize this new graph as a subgraph of the previous one. Okay, so it's hidden here. And for the adjacency matrix of the star product, there is also another formula, to calculate this matrix in terms of the adjacency matrices of J1 and J2, and it's given by this rule. Here, P1, and so P1 is the zero matrix except 1 in the entry corresponding to the root of J1. Same for P2. And then we have this rule. And now these two matrices doesn't commute anymore. So the expectation in terms of this space of matrices who come from some adjacency, which are the adjacency matrix of some graph, you can say they are not independent, but still there are combinatorial way to calculate the expectation. So here, this is I take this slide from a conference in honor to Ira Gessel. So I use his name because it gives me his name is so nice enough to give me a good example. So what I said before is that the expectation, so in classical probability, when two random variables are independent, the expectation of the product is the product of the expectation. So what I'm saying that here we don't have this situation anymore. Still, we can give combinatorial, there exists combinatorial formula for the expectation of product of random variables. Notice that in this case, again, so this G, E, S, E, and L correspond to some matrices. The product of matrices is not commutative. So we are here in front of a case for which the product of the variable, the random variable, are matrices. The product is not commutative, and they are not independent. But still, again, the expectation of product of those monomials can be calculated in a nice way. So here I will tell you how it goes. So for this product, what you can do is to split the factors inside the expectation as soon as they are different. So I can split here, I can split here, I cannot split between the two S, and then it leads me to this result. Okay, so here I have the expectation of S squared because, and I cannot, it's the best thing I can do in this case. Third example, which is the comp product. So combinatorially, it means that I'm going to plug the right factor here onto the left factor on this graph, but just putting a clone of this graph in any vertex by superposing the rooted graph of the second factor into each of these vertices. And the new rooted vertex would be the resulting by superposing the two rooted vertices. Here is again a formula for the adjacency matrix of this comb product. So you see that now it relates the matrix P2 that I showed you before with the A1. Again, those two matrices does not commute, they are not independent, and still there is a combinatorial formula to calculate the expectation. In this case, what you have to do, so here I take like a shuffle of the word Ira and Gessel. What you have to do is to look at, so you start, so let me find, yes. The random variable, again, are matrices, but now you have to consider a total order on the matrices. Here, what I'm doing is considering the total order of the alphabet, A less than B less than C, and so on. And I'm looking at the peaks of the resulting word. So, for example, J is bigger than E, E is smaller than S, S is bigger than E, and so on. So S is a peak, so I put it outside and I repeat the process. So I get with this factorization of the expectation of this monomial. Okay, so again, here we have two examples of spaces of random variables. The product is not commutative, and in some situation, as for the Cartesian product, we end up with the calculation of expectation of independent random variables, and then we can have nice formulas from that. But we also have those other operation for which the resulting, when I want to calculate the expectation of the power of the adjacency matrices of the product of these two graphs, I land with, we get sums of two non-independent variables. And the thing is that we still can perform this calculation. And what's going to happen is that even if they are not independent, what we're going to see is that there exists notion of independence for this very particular type of random variable. So that leads to this is motivation. So what is coming next? I'm going to show you some basic feature of this area called non-commutative probability, who start from the 80s with free probability introduced by Voiculescu, which was interested, in fact, to understand von Neumann algebras. So from some time, he was almost alone in his field until he realized that this had nice application to the study of random matrices, and that makes the field explode, let's say, from the 90s. And from then, there's a lot of people taking care of what is going on this field. At least people from random matrices, for example, also from algebra, and recently also from combinatorics. So here I indicate some of the work of Andrew Nika and Roland Speicher in the 90s, who start to identify some properties of non-commutative probability related to combinatorics, for example, of the pose set of non-crossing partition, the pose set of non-crossing internal partition, and so on. So what is, well, also, let me say, the reason why to look at non-commutative probability is to consider notion of non-commutative independence, for which there are several situations in nature and in mathematical nature for which the random variables are not commutative. So, for example, in quantum mechanics, you can have this relation between the variable for which they are not commutative. The example of free product of group that I will show you in a moment. And I have to say, sometimes I like to see the area of non-commutative probability, not with that name, but with, I like to see it as generalized probability, generalized independence, in the sense that the classical probability theory is inside this area, as you will see. So before giving you the definition, let me recall some of the classical setting in probability. So in a probability space, we consider essentially a sample space, a collection called the event space, and a function, the probability function, which satisfies several axioms. And as soon you have bounded random variables, meaning that this integral is supposed to exist, you can consider the expectation. And the game here is to replace the space of all bounded random variables, which in the classical setting, remember, they are commutative. The product of random variable is commutative. So we want to replace the space of bounded random variables and the expectation map, but by something more general, way more general, which is just one algebra with one linear map. And here is the definition. What is a non-commutative probability space, at least in this talk, will be just this pair formed by a unital associative algebra over the complex. So working over the complex is so far all that we need, and a linear map from A to C whose sum 1 to 1. So this definition is very algebraic, and is not the one provided historically by Voiculescu at the beginning. He was considering also C-star algebras, for example. So here I'm not dealing with this part. I'm treating those non-commutative probability space in the more algebraic setting, which is just an innocent associative algebra, which is a unit, and a linear map whose sum 1 to 1. Okay, some examples. Again, an example of non-commutative probability space is the classical space of bounded random variable with the expectation, which we know is commutative. So in this case, this is the algebra A, which is commutative, but the definition doesn't ask necessarily the commutativity property. Take also the space of square matrices with the normalized trace. That's another example of a non-commutative probability space. So this is an algebra with the product of matrices. One is the identity map, and this map sent, when you calculate this normalized trace on the identity, well, it gives you 1 over n times n, which is the trace of the identity matrix, which is 1. Okay, so this is a very simple, another very non-trivial example of a non-commutative probability space. And also more related to random matrices, the space of random matrices, meaning matrices and full of random variables, for which now this phi is given by this integral. So here, for non-commutative probability space, we have to think on the elements of A as the new random variables, which may commute or not. And this general phi we can think is as the expectation of the non-commutative probability space. Some analogies between this definition and the classical one. So again, the random variable will be the element of the algebra. Sequences of moments will be just they are encoded just by a linear map from the space of polynomials on the variable x to c. So sending this basis element to this particular this evaluation of phi on the element 8i. So this is a time, and also there is the notion of joint distribution of a k-tuple of elements of a k-tuple of random variable is encoded by this map from non-commutative polynomials to C. So sending this monomial to the evaluation of phi on this product inside A. Okay, so there is a clear dictionary. So here I'm showing you just some of the translation between one word and another, but there is a full dictionary on how what's going on the non-commutative probability space with respect to the classical behavior of probability space, or probability theory. So in classical probability, assume we have two random variables were independent that lead us to the calculation of the expectation of the product of powers of both random variable is just the product of the expectation of the corresponding power of the random variable. And the thing is that for there will be notion of non-commutative independence. We don't have this relation anymore, but we will see that we have still some relation which are rich combinatorially speaking. Let me show you a little motivation on what is called the free independence. So free independence is related to this example. So this is a new example. Take this as a new example of a non-commutative probability space. I take a finite group J, and I take the set. I think here is not this. It doesn't have to be finite, in fact. And you take the set of all maps from J to C, with finite support. Okay, and the product between such maps is this. This is called the convolution. Is this sum? So this is nothing else than the dual of the group algebra of a group. Okay. And the expectation so this is an algebra, f of j is an algebra, and the expectation that we're going to consider is the map sending one of these maps to the evaluation of the map on the neutral element. Okay, so that's all. These two data form a non-commutative probability space. And let's look at the following situation. So let's take a sequence of subgroups of J, which are algebraically free, meaning that there are no relation between the elements of pair of those subgroups. And I'm going to consider a sequence of indices, which are so these indices are totally ordered. And if I choose one index, it's different to their neighbors. All right. So for such a tuple, and for such sequence of subgroups, I'm going to take elements I'm going to consider the non-commutative space f of j of those subgroups. Okay, so remember, f of the group is the space of all such maps. All right, and I'm going to suppose that I'm going to take such kind of map for which they send the identity element of j to 0. And now I'm going to look at phi being an element in f of j, of the convolution of the product of such elements. Okay, so by definition, this is the evaluation of this element of the group on the neutral element, this element, sorry, of this map, the evaluation of this map on the neutral element, and by definition of the convolution map is this sum, right? But the subgroups that I take, they're algebraically free, so there's no relation between them, and having this relation just means that there must exist at least one element, one factor in here, which is the identity, in order to get that this product is the neutral element. So if there exists such element in here, say jk, which is the neutral element, I will end up here in this factor with alpha k of jk, which is alpha of a, which is 0. So this sum is parameterized by those kind of factorization. For every of those factorization, I will have one element which necessarily must be the neutral element, leading to that this product is 0. Okay, so the moral in this story is that as soon as I take subgroups which are algebraically free on my group, I look at element on this algebras constructed this f of every of these subgroups, and I look at this the evaluation alpha on the convolution product of those maps. This is 0 as soon every of those maps is 0 when evaluated on the neutral element. All right, so what I give you is again a definition of a non-commutative probability space, and the situation for which if I take those subgroups which are algebraically free, the expectation on f of j of this convolution product is 0 as soon we have this condition. So this is a toy model for what is the free, what means the free independence in non-commutative probability. So what I'm going to do now with this slide is to repeat the previous construction, but in this very abstract setting. So I start again with this abstract non-commutative probability space. I consider unitals of algebras of A, and I say that this family is freely independent if for a choice of an n-tuple of different neighboring indices, then the expectation on a product is 0 as soon every factor of this product comes from such unital subalgebra, and also the expectation of every of these factors is 0. So this is the definition of a family of freely independent algebras, and then a family of elements of non-commutative random variable will be free if the family of subalgebra that I generated with the identity, with the neutral element on the algebra, is freely independent with respect to this definition. Okay, so set of variable will be free if the algebra that they generated are free. And the links with the toy model that I presented before is that if I take subgroups that are algebraically free, then those algebras f of ji will be subalgebras of f of j, and they will be freely independent in the sense of this definition. Now let me give you an example of calculation. As soon we have random variables in this setting which are free. So how to compute mixed moments? What does it mean, a mixed moment? It will be calculate phi of a product of these random variables in A, so element in A, for which I know they are free. So suppose I have A and B free random variables in A, and I want to calculate phi of A times B. So I will use the following trick. I'm going to consider A minus phi of A times 1 of A, and B minus phi of B times 1 of A. So this is, again, the unit of the algebra. So what happened in this case? So if I calculate phi of this term, remember that phi is linear. So phi of this term is 0, and this is inside the algebra generated by A. Phi of this element is 0, and this is an element in the free algebra generated by B, on the algebra generated by B. And I know that A and B are free, so those two terms are free, and phi of those terms is 0. Okay, so if I go back to the definition, so as soon as I have this situation, the expectation of such product of term must be 0. So this product, phi of this product must be 0 because A and B are free. So when I apply the linearity of phi, I end up with this result. So phi of AB is phi of A times phi of B. So not interesting so far because I look at the mixed moment of just two random variables which are free. But as soon as we start to go to more complicated example, we will get to more we will see that it's not the same thing as calculating the expectation of free variables in the classical setting. For example, if I apply the same trick to phi of A1, B, A2, as soon as A1, A2 are free with respect to B, then this is what we get. So phi of A1, B, A2 is splits like that, and I cannot split A1 and A2 anymore because I don't know if they are free between them. All I know is that A1, A2 are free with respect to B. Here are some more elaborate examples just to show you how complicated it can get. So if now I have A and B, which are free between them, if I calculate phi of AB, AB, remember that my algebra is not necessarily commutative, so this is not necessarily a squared times B squared. So I end up with this sum. Okay, so this is just to show you that under this definition of freeness, under free variables, the expectation of those monomials is more elaborate than in the classical setting when I calculate the expectation of free variables. So again, here is a setting for which A and B are free, but I want to look at this mixed moment, and it's not only it's not about splitting. Phi cannot split in this naive way. Let's say is more elaborate than that. Is in this case this sum. All right. So let me now present you some other notion of independence. So I defined you already the free independence. So again, I'm starting with a non-commutative probability space, and here I'm defining what it means to be free, boolean, and monotone independence between families of unitary subalgebras. So for the case of free, I already showed you how it goes. Those algebra boolean independent is if the non-commutative expectation split nicely. In this case, I ask that every of those, as soon as I take one factor, it's different from the one from the neighbors, and it monotone independent. This notion of monotone independence work like that. In this case, again, I didn't put it here, but you must also ask here a total order on the set of subalgebras. So if I can put out AJ because it will be a peak on this non-commutative monomial, let's say. Okay, so just 3 examples of non-commutative independence in this setting, and there are many more, conditional, cyclic, etc. So any questions so far before continuing? No? Okay, so I think I have talked too much about non-commutative probability. I'm going to start now to go up to combinatorics. So here again, another example. So here's my first combinatorial slide, let's say. So those are a compilation of the example that I show you. And the magic here is that as soon you have free variables, you have those monomials formed by free variables. And so in this case, on those examples, A's together are free, B are free, C, and so on. So, for example, if I join the family of free variable, the A with the B, I have this crossing. If here I join the A's together, the B together, the C, the D together, so as soon as I make this process and I get non-crossing partition, non-crossing, then phi split nicely. So you will have just one factor. And as soon as you have splits, you have crossing, then they will split on sums of product. That's what this sentence means. Okay, so here's, let's say, the magic now appearing on the study of formulas for the expectation of mixed moments, in this case involved with free. In this case, those examples come from free, the free independent. All right. So some notation before going to my next slide. What I'm going to consider is, so now in this theory, we also want to consider cumulants and moments associated to this non-commutative independence. So the moments will be easy. What is not so trivial is the cumulant. So what we would like is to have analogues of cumulants on those non-commutative settings, which are nice in the sense that if you look at why we use cumulants in classical probabilities, because they are easier to handle calculations, so they are additive, they write nicely in terms of moment, and those kind of properties we want to have also for this non-commutative independence relation. So what I'm going to show you now is some formulas on the free, boolean, and monotone cases for which we can relate moments to cumulants in that setting. In order to do that, let me introduce the following notation. So as soon we have a families of multilinear functional like this, and a partition, a non-crossing partition, f pi evaluated on A1 to AN, on those elements will be the, as before at the beginning of my talk, the product of f sub the size of the blocks are now evaluated on the element of the block. Let me show you an example. So an example is better than words. So I have my previous non-crossing partition called pi in this case, and if I have a family of multilinear functional, f1, f2, and so on, so fi has a domain 8 power n I, so f pi of this sequence will be the product of f sub the size of the block evaluated on the element of the block. So for this one, I will have f4 evaluated on a2, a3, a4, and 5, and so on. Okay, so with this notation in mind, I present you the formulas from moment to cumulant in every of those three examples that I gave you: free, boolean, and monotone independence. So remember that phi is the expectation. So we have phi of this monomial, non-commutative monomial, is related to its associated cumulant through these formulas. Here, so here what we recognize is the new cumulant formula that I present you before, or let's say moment, because here I don't have Möbius terms, right? So I'm writing the moments in terms of cumulant on each situation. So for monotone, I'm also using non-crossing partition, and I have to multiply by this special term. So this is the factorial of a 3 associated of a partition. We're not going through that, but just want to show you the relation between moment and cumulant under this new perspective of non-commutative probability. All right, so now let me tell you why Hopf algebra entered to the scene. So the way I will use Hopf algebras in this case is through combinatorics, based on the work of Nicole Johnny and Giancarlo Rota, who look at Hopf algebras in the following sense. So the product is just a mechanism to take one combinatorial object, two combinatorial objects, and merge it together to get a new combinatorial object. And dually, the coproduct is intended to a combinatorial way to split one combinatorial object in two in all possible way that the coproduct allows you. All right, so let me give you an example of, well, first, a very quick definition of what a Hopf algebra is. So it's just a vector space with a product rule forming an algebra, associative algebra, and a coproduct rule forming a co-associative coalgebra, such that both rules are compatible, and for which there exists something called the antipode, which is nothing else that, so we take the space of all linear map from the vector space H to itself, and we consider this product called also convolution, which works like that. So and here again I have a typo, I should have delta. So I apply the coproduct, I will have possibly a sum of two terms. I apply F and J, and then I multiply everything together. Okay, so this form an algebra, and not every time we have any element in here has an inverse, but when the identity map has an inverse, it's called the antipode, and when the antipode exists, then we say that H is a Hopf algebra. So with all these three items, we say that H is a bialgebra, and then if such inverse of the identity exists through the convolution product, then this vector space is a Hopf algebra. Now let me show you a combinatorial example. So for example, we have a Hopf algebra of binary trees. So here I'm just showing you an example of product and the coproduct. This is, if we want to be very, very formal, this is the dual of the Hopf algebra, of the original Hopf algebra given by Lode and Ronco. So here the terminology is that, so let me start with the coproduct. I have a binary tree T, and the coproduct rule is split the tree, choosing one leaf. So you choose one leaf and you walk into the root, and that split the tree on two parts. You do that in all possible way, meaning that which means you choosing all possible leaves lead you to split the tree in two, and that will be the terms of the coproduct. And for the product is kind of a shuffle of the trees. So you have to split the second factor T in such a way that the number of times internal vertex you have on S, and that will lead you to this sum. Okay, so this is a combinatorial example of a product and a coproduct that in fact form a Hopf algebra. Now the Hopf algebra that I'm going to need in this talk is a little bit more elaborate. It's called the double tensor Hopf algebra. But instead of showing you all this formula, let me show you some example. So this Hopf algebra will consist on a product and a coproduct, and it's called double tensor algebra because of the construction. You start from a vector space V. You take the tensor product, and then you take the tensor again. And combinatorially, you can think of that on a vector space of words on non-empty words. Okay, like here. So every W is a word of letter in your vector space, and then you form a big word on that, separated every word W by a bar. So this bar refers algebraically to the external tensor product of this T here, and then every internal W is a word, is a sequence of tensors with respect to this T. Okay, so let me just keep those two slides. So there is a product and a coproduct. The product is very simple. It's just put a bar between U and V. So if U are a word on words, V is a word on word, you form a new one, just concatenate them. And the coproduct, let me just show you an example. Again, this comes from this nice workshop dedicated to Ira Geisel. So here I have this is an example of a word, a letter, say, in this Hopf algebra. It's a non-empty word, and this is a word on word, or a phrase. Sometimes I like to call it a phrase. So this phrase has two letters, this word Ira and this Geisel. So the coproduct on a word is just you select subset of letter and you put it on the same order. But if you select some letters and there are some holes, so if you select, for example, A and C, between A and C there are some letters, right? There's this sorry, it's the other way around. Let me select just B. If I select B, I pull it apart, and then I end up with the rest of the letters, but B was between A and C, so I have to put a bar because it gives putting away B, let a hold on my original word. Okay, so it's if you know about the shuffle of words, it's essentially the same thing, plus the fact that you have to put a new bar as soon you leave some holes in your original words. Then when you calculate the coproduct on a phrase, it's the same thing, and you have to leave the bar that you had before. So in this example, I select R, S, and L. There I put it in this part, and then you have A and I in this part, but there is a hole leaded by R, so you have to put a bar, which I think I forget also. So you have to put this bar here, and then you have GE. So oh yeah, so that was the punch of this slide. There is a mistake, but then I corrected. Okay, so there are the other bars I have to consider. So I think I have 5 more minutes. Hello?
Sure.
Yeah,
I mean, yeah, we usually do 15 minutes to an hour, and I think we're just right at an hour.
Okay, so
right now.
okay, yeah. So I think I will end up in max 5 minutes. Is that okay?
Sure.
Okay, so I just present you this new Hopf algebra. So what is the relation with the moment to cumulant formula that I showed you before, coming from this setting of non-commutative probability? So here's the receipt, let's say. So what this is from a construction of Ebrahimi-Fard and Patras, and so there's some magic that will come, and the magic is that you take this Hopf algebra of non-empty words, you replace. So I start with a non-commutative probability space, any non-commutative probability space. Okay, so now the role of V before is played by A. So I calculate the double tensor algebra on A, meaning that I will construct words using the letter of my algebra of non-commutative probability space. And the coproduct that I showed you before has a nice property. It's called codendriform, meaning that you can split it in 2 parts, which are not co-associative anymore, but they are related in a very nice way. And then when you look at the dual, the space of linear maps from H to K, this coproduct and these splittings becomes a splitting of a product of the dual of delta. And then what happens is that you can define a new, let's say a new non-commutative probability space now on H. And now the non-commutative expectation, here come phi, is such that when you restrict it to every letter of the double tensor algebra, so now a letter in the double tensor algebra is just a non-commutative word, it restricts to the non-commutative expectation, which I start before, evaluated on this word. So what this is just a generalization, I start from a non-commutative probability space, I consider the double tensor algebra, and from this little phi, which is a non-commutative expectation, I construct a new expectation now from this bigger Hopf algebra of words on non-empty words. Okay, so and what can I do with this? Well, I'm going to look at the set of characters, which are maps, multiplicative maps from my Hopf algebra to K. And it's well known that this form a group with the convolution, and the inverse can be calculated through the antipode of the Hopf algebra. Okay, there are other more subtle set of characters called infinitesimal characters who satisfy this property, and just for people who are knows about differential geometry. One, so the set of characters is a group, and the infinitesimal character is a Lie algebra, and it's the Lie algebra associated to this group. Okay. Now here is the relation. If you take infinitesimal characters coming constructed from the double tensor algebra, starting from A, and you want to solve those identities, those equations. So here you want to look at rho, kappa, and beta who satisfy these three equations. Then the solution are precisely the monotone, free, and boolean cumulant that I showed you before through those formulas. So, for example, so here there are three ingredients. There are those are equations on characters. This is the dual of the delta that I defined you before, and those are the duals or every of the splitting of the deltas. And for example, if I take what I'm saying here, if that the solution rho of this equation is exponential, evaluated on a word of letter on A, will be exactly the monotone cumulant evaluated on this word. Same for kappa and same for beta. So just to show you one result, and I will end the talk. So we can isolate kappa and beta from the previous equation. When I do that, I end up to look at the inverse of this big phi, now this new non-commutative expectation. And as I told you before, the inverse can be calculated through the antipode. So the antipode leads you a way to calculate this inverse. And as soon as you know this inverse, you can have formulas for kappa and beta. And so that's the result. That's one of the results that I mentioned before. So what we did was to calculate a cancellation-free and grouping-free formula for the antipode of this double tensor algebra in terms of Schroeder trees. And as soon from this formula, we can have recover a nice formula for those cumulants for these free and Boolean cumulants, again in terms of some class of Schroeder trees called prime and Boolean, so it's just a quick way to recover those formulas in terms knowing now the antipode of this double tensor algebra. So I think my time is over. Let me just finish by saying that there are many more combinatorics related to that. So as you see, I just have time to tell you a little part of the story. I will go now to my last slide. Thank you very much for your attention. And if you are interested on hearing more about non-commutative probability and the relation with combinatorics, you should look next year at this workshop that we are organizing at Vienna. So keep in touch if you are interested to attend. It will be the second to last week of February. Thank you very much.
Thanks so much, Yannic. We have a little bit of time for questions.
Sure.
Anyone wants to start us off? Maybe we had some people that had to go.
Yeah, sure. I end up. Yeah.
No, that's okay. That's okay. I have a question that I'm trying to formulate, but I'm just thinking about the new words.
You mean the tensor algebra or?
Yeah, I think I'm just like trying to settle into the definitions in order to formulate a question.
Oh, okay, yeah, sure. Can go back. Okay. So this double tensor algebra is. So again, you take so you start with a vector space V, and so let's say let me write it here. So this is the direct sum for n bigger than 0 of these terms. Okay, so it's the direct sum of all these components. So what we have here is that, so here you have a word. So I should put here a bar, let's say. So this will play the role of the bar because there are two kinds of tensor, right? Because I'm taking twice the tensor. So here you have a word of length n1, then you will have a word of length n2, and so on. And they're separated by these bars. And again, those bars refer to the tensor product at this level. See, so if I have a vector space V, an element and some vectors, so I can have V1, so say V1, V2, V3 bar, V4, V5. What I mean is V1 tensor V2 tensor V3, and then this external tensor V4 tensor V5. But again, combinatorially, you can see it as just take this would be, you take an alphabet, take any alphabet, a non-finite set with a total order, and you can consider the free monoid on that. So it's all words obtained by concatenation. But now it's like the free monoid on this free monoid, but taking away the empty word. So you have words of words. Every letter of these new words is a word constructed from your initial alphabet.
Okay. Yeah, that's very helpful. Thank you. Yeah.
So again, I didn't talk about, for example, the proof of how to relate characters of this Hopf algebra with those moment to cumulant formulas, but the proof is by recursion, let's say. But it's very it's amazing that just one Hopf algebra leads to 3 different non-commutative independence, and leads to 3 formulas from moment to cumulant of 3 different independence notion. I see also some.
It's mainly just people thanking you. Yeah. Well, I think I'll stop the recording now, but thank you again for a great talk. This was awesome.
Thank you.